Hi, chemistry. Today's topic is a big one, okay? It's called the equilibrium constant, and it's got a symbol Kc. So I'm going to call it Kc, just means equilibrium constant. And what it is, it's a mathematical relation that helps us predict concentrations in a chemical system once they reach equilibrium. Eventually, we're going to use Kc values with an ice table to do some pretty impressive work. All right, but I got to show you how to find out what Kc is. Okay, check this out. I already made a big mistake, but I left it in there because students make the same mistake. So for a reaction, this is in general form, and it may not make any sense until you see like a real example, which will come right after. So if this is my reaction equation, or my chemical system, Kc, you take the concentrations of the products. So remember, square brackets mean concentration. Okay, so the capital letters are the actual chemicals, and the lowercase letters are the coefficients. You take the concentration and raise it to the power of the coefficient. Start with products, multiply them together, divide by reactants. Okay. Again, if that doesn't mean anything to you, just check out this actual example. So I want us to write the Kc expression for this. Nitrogen monoxide combusting to form nitrogen dioxide. And I'll just show you how simple it is. So just remember to start with the products. It's the concentration of NO2. Remember, that's what square brackets are. And the exponent is the coefficient in the reaction. There's only one product, so I only include one thing in my expression. The reactants go in the denominator. So it's going to be the concentration of nitrogen monoxide squared times the concentration of oxygen gas. No exponent there because there's no coefficient, or coefficient of 1. That's what Kc looks like for this system. The numbers are going to come later, but I want to show you it's really simple to write down a Kc expression. The most common mistake is to put the reactants on top. I did that in my explanation, but that's no good. I crossed it up. Always remember products on top. Moving on. Just some facts about Kc. All right. Kc for reverse reactions are the inverse of each other. And I will absolutely ask you a question like this, or where you need to know this to get it right. So, say this reaction here, if it has a Kc value of 5, just reversing the reaction is the inverse Kc. So this reaction would have 1 over 5. And I mean, mathematically, that makes nothing but sense. Okay, Kc for this one would be this divided by these two. If you reverse the reaction, you just flip the fraction of Kc. That's why they're inverse of each other. That should make sense. Let's see what else we got. This will become more important when we learn about Le Chatelier's principle. I just like saying Le Chatelier. It's coming up. The value of Kc depends on temperature, and we'll see how when we get to that Le Chatelier's principle. Okay? Initial concentrations of things don't affect Kc. Kc doesn't care about that. But a value of Kc will change if the temperature changes, and that's going to be on some kind of assessment later in the course for sure. All right. I'm going to try to help you wrap your brain around this. Kc is all about concentration changes. Okay, so in a chemical system, you only need to consider entities that are gas or aqueous and not liquid or solid. In my next video, I'm going to try to convince you of that. Essentially, particularly with a gas, it's fairly simple. A gas takes up the volume of its container. So if you take away some of that gas, the concentration goes down. Same with an aqueous solution. Okay, if you dissolve something in a sample of solvent, like water, it will take the volume of that water. If there's less of the solute in there, the concentration goes down. Or if you add more, the concentration goes up. But for liquid or solid, if you change the amount, you also change the volume. So it doesn't actually affect the concentration, and I'll try to convince you of that in the next video. But I want to show you how to apply this. Because at the end of the day, you just have to remember that you only care about gas and aqueous solutions. So if I'm writing Kc for this chemical system, I got ammonium chloride turning into ammonia and hydrochloric acid here. Remember to start with the products. They're both gaseous, so that's good. It's going to be the ammonia concentration times the HCl concentration. This is solid. So forget about it. We're done.